The purpose of this demo is to get us ready for part E. We're asked, what is the electric field at the midpoint between these two charges, Q1 and Q2, due to both charges? Now folks, this formula for electric field only has place for one charge. I'm looking for the electric field at this location due to Q1 and Q2. What do I do? Do I add them together? Do I average them? Do I subtract them? Do I multiply them each by pi and divide by 4? What?
Since they're vectors, wouldn't you just add them?
Ah. Each of these is going to give me an electric field that is a vector, and we just add those vectors. In other words, we use superposition. We admit that we can only solve a problem with one source at a time. So what we do is we first of all pretend that Q2 does not exist. And we calculate the electric field due to Q1 alone. And so in this formula, I would put Q1. And it's to the right because it's away from the positive source. The next thing I would do is I would pretend that Q1 doesn't exist, that the only source is Q2. And I would find the electric field at that X due to Q2. Notice that it's twice as big because the magnitude of that charge is twice as big. And it's to the right because it's towards a negative source. And then, once I found the electric field due to each part, I add them together to get the total. When we were talking about the electric field in the room due to the floor and the ceiling, we had a field up due to the floor, we had a field up due to the ceiling. The total field was the sum of both. In the chamber, we have a field up due to the positive bottom plate. We have a field up due to the negative top plate. We have a total field that is the sum. Superposition is the one theme that's going to transcend all the boundaries in this class, in this semester. We used it when we had two pulses that were approaching each other on a spring. We're going to use it over and over and over again with electric fields and forces. Okay? Long ago, I used to make a joke of this, and I'd say, you know, if you've got a problem you can't solve, you stand up and you say, "Hi, my name's Greg Francis, I've got a problem." You know, kind of mocking the AA meetings and talking about how you take the big problem, break it up into small problems. Well, it got back to me about 5 months later that at every AA meeting in Bozeman, people were getting up and saying, "Hi, I'm Greg Francis, I've got a problem." And then everyone would laugh because they'd all taken my class. I don't know if I was driving them to drink or what. Anyway, so I stopped. I don't do that anymore. Okay. Now, if we calculate those individual fields, the field due to Q1, notice I put Q1 in here, and notice also that the distance now is 10 centimeters, not 20 centimeters, because it's always the distance from the source to the X, where I'm finding the field, and that's only half the distance. I find 2,700 newtons for each coulomb. When I do it for Q2, notice I don't put the minus sign there. And notice because my charge is twice the magnitude, I get a field that's twice the magnitude, or 5,400 newtons for each coulomb. Since they're both pointing the same direction, I add them, and I get 8,100 newtons for each coulomb. Okay, is it making sense? Is it all coming together? Now, once I have that field at the center point, I can put a test charge there, a Q3, if you will. In this case, we happen to put a negative test charge, but Q1 and Q2 have done their job. They did the first step of this two-step dance. They created the field. Now we don't need them. Okay? We get rid of them, and we just worry about the force, the actual push, that's exerted on this negative test charge, this negative captain curve. Now, if the field is to the right, and the test charge is being pushed is negative, then the push, the actual force, is in the negative right direction, or the left direction. It would be opposite the electric field. Opposite. Okay? And the size would be given by the definition of the electric field. Notice I don't put the minus sign here because I already know the direction. I just want to know the magnitude, always a positive quantity. And I get 0.016 newtons. Okay, I hope some of you are bored. I hope most of you are bored. Now, let's skip the last part here. Okay. Let's see if we understand. 2 point charges plus Q and minus Q are fixed in place, a distance 2d apart is shown. Now folks, typically we're going to take our Klingons, our sources, and we're going to nail them to the table, or we're going to super glue them to the table so that they don't get pushed and change the problem. Okay? So in this case, they're fixed at those locations, and we're asked what is the direction of the electric field at the midpoint between the charges. Now student 2 says, I think we've all come to realize that student 1 is always wrong, but student 2 sometimes is right. The electric field is given by this Coulomb's law, so if I do the calculation with my calculator, I get a positive contribution here and a negative contribution here, so the electric field is 0 at the midpoint. What do you think? Wrong or sick and wrong? Sick and wrong. That student is misinterpreting the minus sign. The minus sign doesn't mean right or left. The minus sign means towards. The plus sign means away. And typically we ignore the minus sign and just use our gut. And so, since I've got an electric field away from the positive, that would be to the right, an electric field towards the negative, that would be to the right, they would add. They would not subtract. Okay, with your clicker, I have two identical positive charges, A and B, and they're fixed in place at these locations. The distance from point C, location C, to charge A is twice the distance as from location C to charge B. What's at the X? Nothing. Empty space. Okay? We pretend there's 1 Coulomb when we're finding the electric field, but in truth there's nothing but empty space. The X is a placeholder, an address, a mailbox. Now, which of those directions gives the direction of the electric field at point C with your clicker, people? Okay, get done.
It does matter because you've got points. It's going away towards the technology. It's going back.
Okay. The correct answer is C. Now, If we look at the contribution due to this positive source, it will be away from the positive. And I drew it at some arbitrary length. If I look at the contribution due to this positive source, it will be away. And because it's twice as far, the effect will be 1/4 as great. And so the electric field will be 1/4 the size as that due to B. The total will be like that, or C. Now folks, I have 2 minutes left. With those 2 minutes, I'm going to help you with your tutorial homework. These are important 2 minutes. This formula, Coulomb's law, only applies when your source, your Klingon, is concentrated in a small location, at a point. If you have charge that is smeared over a larger area, like this hemispherical rod, what you can do is break it up into chunks, like chunky peanut butter. And in this case, I broke it up into 9 chunks. You could break it up into 1001 if you're bored, but 9 is enough. Each of those chunks has 1/9 of the total charge. Okay? Now, if I want the electric field at the X due to all of this charge, I just use superposition. That's the electric field due to that one. That's the electric field due to that one. As I move around the hemisphere, I get that contribution, that one. That one's due to the one at the bottom. Okay? Now, if each one of these contributions is 5 newtons for each coulomb, I just made that number up, and I've got 9 of them, do I just take 9 times 5 to get 45 as my answer?
No.
No, because some of them are fighting each other. If I were to add these 2 contributions, this one gives me that one, and this one gives me that one, I get 0. They're opposite directions. If I were to add these 2 contributions, this one due to that one, this one due to that one, I get almost 0, because they're mostly in the opposite direction. If I look at those 2, I get something bigger than 0, and those 2 even bigger, and that's the one on the bottom. And you see that total is less than if I had all of that charge at one location. If I were to scrape all of this charge down into one glob, I can think of that glob as being 9 globs, each giving me 5 newtons for each coulomb. Since they're all giving me contributions in the same direction, now 9 times 5 is 45. So I get a bigger field when all of the charge is concentrated than when it's spread out over a region. Okay, that's all the time we've got. See you on Friday.